Hello, chemistry students. It's Professor Sean McMahon, and we will continue today with our second lecture of Chapter 2, which is essentially measurements and the math involved with chemistry. So with Lecture 1 last time, we covered the concepts of our basic math review with significant figures, how to determine the number of significant figures in measurements by using the precision of the instrument, how there's always an estimated guess for the last digit that we called kind of the doubtful digit. We talked about exact numbers and measured numbers, how they're with an exact number, we don't use those for significant figures because it's unlimited. With measured numbers, we have to use the precision of the instrument. We also talked about how to perform calculations and determining the amount of significant figures for the final answer, and rounding when necessary, and using scientific notation. So today, we're going to continue our discussion with, again, math review, but now we're going to use our measurements that we take in lab, use those measurements, combine them in calculations, and for problem-solving techniques. So we're going to go over the different types of measurements. And again, the focus when we talked about OHEC, the scientific method, OHEC standing, if you guys remember, for observation, hypothesis, experiments, and conclusions. In our experiments, we collect data, and typically it's quantitative measurements. So we'll talk about the different types, their units. We'll have to review the metric prefixes because typically in science, we're going to use the metric system. And I know here in the States, we don't, but because this is a physical science course, we are going to use the metric system, and we have to learn to convert within the metric system, which is actually easier, and within our own system, the English to English system. And because we have to be able to convert, we'll get comfortable using what are called conversion factors. They're basically equivalent ratios from one unit to another. An example that we use that's common, it doesn't matter where, is in 1 minute, there are 60 seconds. That is a conversion factor where you convert minutes to seconds. Dimensional analysis, also unit analysis, sometimes called the conversion factor method, or just basic problem solving, where we're going to use these conversion factors as ratios and use their units to cancel out what we know and get to what we need to know in our problem solving skills. So the first thing is, what are some basic units of measurements? Or you can even think of what are the basic types of measurements. So typically we're going to measure length, right? So that's, you use a ruler. We're going to measure mass. So mass, we would use a scale, right? There's different types. There's your basic top loader scale and your analytical balance, but you'll be using scales. They don't have volume on here, but a lot of your glassware is primarily for volumetric measurements. Then you have things like time and temperature. And for the international system, the standard units, for length, you use meter, mass, kilogram, and seconds, Kelvin. And you'll see that the kilogram and the meter is not typically what we use here in the US. It's not an issue. I will go over, though, that system, but you will have to be able to convert not just within the English system, which is our system, between the English system and the metric system, which is what you see here with meters and kilograms. So this is our system. I always like to kind of show our system because it shows length measurements. I have right here volume, mass. Really, weight is more accurate of a definition because mass doesn't change, but the weight does based on the gravitational force. Time is pretty consistent around temperature. Here in the States, we use Fahrenheit. We'll talk about how everywhere else they use Celsius. And then speed, which we do miles per hour, because when we look at length, we use miles, right? So when you're in sports, you're running the mile, right? 4 laps around the track. They're not telling you that a lap is, basically 440 meters, right? But the way it works is typically with our system, if you flip over your driver's license, right, it's going to say how tall you are and how many inches. So like me, I'm 6'3". Okay. If you play football and you have a longer distance, right? We got a 100-yard football field, but there's 3 feet. Like I said, if you're running a mile, that's 5,280 feet. You should know these because they're part of our system, and you should be able to interchange between them, okay? Now, the volume's a little trickier. People aren't used to reading cookbooks and things like that like we used to, but 8 fluid ounces is 1 cup, right? So if you have a cup as a unit for a recipe, that would be 8 fluid ounces. 2 cups is a pint. Now, you can think of that as 16 fluid ounces, right? Because 8 ounces make 1 cup, so 2 cups would be 16. 2 times 8, 16. So a pint, 16 ounces. 2 pints is a quart, and 4 quarts to a gallon. An easy way that we remember this when I was a kid, they would talk about 4 quarters to the gallon. I know people don't tend to carry a lot of change in their pocket, but 4 quarters equal $1, 4 quarts to a gallon. Weight, again, 16 ounces to a pound, 2,000 pounds in a ton. But what you kind of see with our system, it's all over the place. I actually think this is a more difficult system because there is no consistency in the numbers. However, we still use it. We're one of 3 countries, and we haven't converted completely to the metric system yet, which is a little surprising. So out of approximately 193 countries, there's only been 3 that haven't adopted the metric system. Everybody else uses the metric system, which we have to learn. So those countries, America, Liberia, and Burma. These are the only 3 countries that do not use the metric system. Now, that's okay. But again, we will be using the metric system. So one of the things that is kind of nice about the metric system, to avoid these numbers being all over the place, like 5,280 feet in 1 mile, 3 feet to a yard, all these random numbers, we use prefixes to dictate a specific quantity, and that quantity is the same. That ratio is consistent. So it doesn't matter if I'm going to do mass, volume, length. I use a prefix to tell me my ratio, okay? And why can we do this? Because the prefix is some multiple, or you can think of some factor of 10, okay? So we use base 10. The reason why this is nice is when we go back to last lecture and we talk about scientific notation, we had the exponential notation base 10. We can just move decimals around to figure out the correct exponent. So here's an example. The prefix kilo is 10 to the 3. That means it's 1,000 times bigger than that standard unit. So if the standard unit, the unit we'll say at the ones place is meters, a kilometer or a kilo is 10 to the 3 times bigger, okay? It'd be the same if we were doing mass. 1 kilogram is 1,000 grams. And remember, 1,000 is just 10 times 10 times 10. That's where we get 10 to the 3 zeros. And because the kilo is bigger than the standard unit, that's why the exponent is positive. Now, tera, because of computers, people are becoming more and more, familiar. Terabyte. So that's 10 to the 12. Okay, that's a much bigger number. So here are your prefix multipliers that we'll be using in the metric system. Now, I just mentioned kilo, right? So kilogram, kilometer, it doesn't matter. That prefix kilo means it's 1,000 times bigger than the standard unit. So your standard unit could be, again, either meters, grams. So this would be for length. This would be for weight or mass, and for volume, it would be liters. Okay. Mega, right? So mega is 10 to the 6. So that is 1,000 times larger than a kilo. But again, instead of writing out 6 zeros, we can just say it's basically 1 times 10 to the 6. giga, used to be gigabytes. That's not enough now, but that's 10 to the 9. So we're seeing that this is going up multiples of 10 to the 3 from the baseline. Tera, 10 to the 12. Peta, 10 to the 15. Now, these are all larger than your standard unit. That's why the exponents are all positive here. Where it gets a little tricky for students or people in general is when the prefix means it's smaller than the standard unit, because when it's less than the standard unit, we end up getting the negative exponents. So that sometimes messes people up. So deci, okay? A decimeter is 1/10 of a meter. That's like saying 1 to the 10, 1 divided by 10 to the first. And if we follow our rules of exponents, right? If you have an exponent in the denominator and you want to bring it to the numerator, to move it up, it becomes negative. So centi, 0.01, what does that mean? That's in the hundredths place. It's 1/100th of a meter. If I said centimeter, it's 1/100th of a meter. And 1/100th is like 10 squared. So 1 divided by 10 squared, which if I bring it to the numerator, that's where I get my -2. Milli, it's 1/1000th. Right? And then it goes like the larger prefixes by multiples of 3. Micro, it's 1/1,000,000th. Nano, billionth. Pico, -12. Femto, -15. Now, you do need to memorize these, but I'll be honest, you primarily, for my class, I like to have people know kilo down to nano. Now, why am I picking those? Well, because when we study, the atom, we have to talk about electrons and their locations, and we learn that using light. And typically visible light is measured in nanometers. You may have also heard of nanotechnology, just like microbiology. So it's in my opinion that to me, this is important. Those are the ones I want you to learn. The other ones, typically, I'll be a little more free and provide those conversion factors. Now, a lot of people don't like this negative conversion factor. So you will also see that there is a positive form of it. So instead of saying 1 deciliter is 1/10 of a liter, which is 10 to the -1 liter, you could just say there's 10 deciliters in 1 liter, like right here. Now that's keeps it positive, right? Just like I could say there's 100 centimeters in 1 meter, right? So if a centimeter is 1/100th of a meter, why not say, well, instead of having 1/100th of a meter, right here, I'll say 1 meter is 100 centimeters. Now, what could we do to help us make these negative exponents positive? Well, think of the prefixes. Deci, how many years in a decade? 10. Centi, how many years in a century? 100. Un mil, a millennium, right? How many years in a millennium? Oh, they didn't write it here. 1,000. So you could write there's 1,000, I don't know, milliliters in 1 liter. Micro, 1,000,000. So you can make these positive too, okay? The other thing you're going to need to know is, how do I go from one system to the other when I need to? I call them bridges, okay? So one bridge that's an actual exact measurement is 1 inch to 2.54 centimeters. So for length, I tell students to know that. Now, there are other ones. So for a lot of you, you may be comfortable with converting kilometers to miles and vice versa, right? Or 1 mile is 1 point, right? This is a little more common. 1 mile is like 1.609 kilometers. That's why a 5K, 5 kilometers is like 3.3 miles or something, if you ever ran a 5K, right? But the reason why I'm saying no this one, because one, it's exact. Two, when you're in a lab, we're not measuring miles, right? You're going to measure the length of an edge of a book or maybe a phone or, so we're going to be dealing with inches and centimeters with a little ruler. So it just makes sense, since that's in the ruler, let's focus on that. Now in lab, right, you could know kilograms of pounds. Like if you watch maybe boxing or something, they talk about kilograms to pounds or stones. We're not measuring kilograms of things. We are measuring grams. So I say the bridge you should get comfortable remembering is, and I even tell students, you can use the bridge, 1 pound is roughly 454 grams, right? You can use that, okay? The one that's tricky is 1 liter is 1.057 quarts, roughly. And that's, we're actually getting comfortable with the liter because thanks to the 2-liter bottle. Okay, but those are your bridges between our system, which again, only 3 countries use the English system, right? US, Liberia, and Burma, and they're using inches, pounds, and liters, or actually, I'm sorry, on this side, it's quarts. And we want to move it to the metric system where all the other countries use, which are, centimeters and grams and liters, okay? So how can we do this? We create a conversion factor, right? Or a unit conversion or a unit factor. I actually call them ratios, right? They're just ratios. It allows me to go from one unit to another. So an example, I said minutes to seconds. Most students are really comfortable with this, right? 1 minute is 60 seconds. Well, 1 milligram is 10 to the negative 3 grams. Why is that? It's 1,000th of a gram, which again is 1 over 10 to the third of a gram. But if I want to bring this exponent to the top, it becomes negative. It's smaller than a gram. If you don't like that, for milli, you can just say there's 1,000 milligrams in 1 gram. But essentially what we're doing is we're changing one unit to another because they're equivalent. So they typically come in pairs. So how can we write them as conversion factors or ratios? Like that. Now, the reason why I like writing them across, you'll see that this, when I do problem solving, it helps me cancel units out. I call it basically like the railroad tracks. It helps me make railroad tracks and cancel out units, okay? So again, when we're doing these relationships, do not use the backslash when you're writing it out. Write a bar straight like this. The other thing is, in this ratio or this quotient, because 1 minute is 60 seconds, it's, as far as time goes, it's the same amount of time. It's whatever it is. You can flip it because they're equivalent. Okay. Now that's very powerful because it'll help me cancel out the units that I need to cancel out. So how am I going to use conversion factors and solving problems, which is referred to as dimensional analysis? Okay. Now, typically with dimensional analysis, for some students, it takes a little bit longer. Just work at it. Once it clicks, it'll click, but it might take you a little bit longer if you haven't used dimensional analysis. Okay. So the first is I have to figure out what's given to me, the known quantity. Sometimes I call it the given. And I have to determine the new quantity, what it's asking for. I call it the want. Okay. So what do I start with? What am I given? And what do I want? And how do I get there? Well, the bridge of getting there are these conversion factors. And then I'm going to multiply all the conversion factors needed to cancel out units to get me to where I need to go. And then obviously I'm going to use my calculator. We went over how to use scientific notation and how something is in the denominator to use our parentheses. And we're going to solve the problem and make sure the final answer has 3 things: the numerical value, the correct sig figs, and the units. Those were the three. So let's do one that we're comfortable with. How many seconds are in 3.55 minutes? So what am I given? Well, it's obvious I'm given 3.55 minutes. What do I want? How many seconds? So I want seconds. So I need to go from minutes to seconds. So what conversion factor allows me to do that? Well, I can use the 1 minute per 60 seconds or the 60 seconds per 1 minute. They're the same thing. Which one am I going to use? Okay. Well, I have two choices, right? If I start with this choice, we'll say choice number 1, minute times minute over 60 seconds. The minute here doesn't cancel with this denominator unit. And you can think of it as, you know, it's like a reciprocal property. Like if I had 3, how would I cancel that out? I would want 1/3, right? I want to cancel that out, and now I have 1. Well, it's the same thing with the units. I want to be left with, you know, the unit on the top, but if I do it this way, seconds and minutes don't cancel out. If I do it this way, right, the minutes actually cancel out because now it's in the denominator here, it's in the numerator here, it cancels, and it will leave me with 60 seconds, or seconds rather, as a unit. I still need to multiply the 3.55 by 60. So that's what I would do. I would make sure that the conversion factor between 1 minute and 60 seconds allows for the minute when I'm given. So you can think of it as I'm given 3.55 minutes. Before I even write the numbers, I want to get rid of minutes. I need to have that in the conversion factor on the bottom. Okay, and I can convert the minute to seconds, so that goes on top. And then I could worry about the numbers. 1 minute, 60 seconds. And that's what I did here, and it cancels. Now, the next thing is once you perform the operation, right? 3.55 times 60, we're not using this for sig figs because we're treating it because it's within time as an exact conversion factors. What are we using? We started with 3.55 sig figs. So that's 3 significant figures, if you remember, because there's 1, 2, 3 non-zero digits. So my final answer should have 3 sig figs, which is 213 seconds. So what does this have? The correct numerical value, correct sig figs, and the correct unit. Which makes sense, right? Because 3 minutes is 180 seconds, because 6 times 3, 180, and another half minute, 30 seconds, 100, 210. You can do the mental math almost and check your work to make sure you're right. And I would tell students, always do a little bit in your head to see if that number 213 makes sense. So the 2 digits in 60 seconds don't affect it. Neither does the 1 digit in minute, because it's an English to English. It's an exact conversion factor time, right? You never use 1 anyways to determine sig figs, but in this case, we're treating it as an exact number. So all of the English to English, right? So all of these are our system. All these conversion factors, we don't use the numbers, we treat as exact. Right? I didn't measure this out. I just know it. It's an exact number. So this is the English system. So English to English. Our system of units. So we go from feet to inches. We don't use that to determine sig figs. In the metric system, if I'm going metric to metric, kilometers to meters, I treat that as exact. So I never use exact numbers to determine sig figs. And again, another example of exact numbers, counting numbers, 28 students, exact conversions, or the 1 in any conversion, okay? Now, if I'm going from the metric system to our system, they're not exact. We're not going to use the 1. So, but in that case, because these are approximations, we're going to use these numbers. So this would be 3 sig figs, 1, 2, 3, and this leading 0 doesn't count. It's only used for placement. And then we have 1, 2, 3, 4. This would be 4 sig figs. If that causes you difficulty, go back to lecture 1 of chapter 2, and that should help you out, where we talked about sig figs. There's only one exact metric to English conversion, and that's the 1 inch to 2.5 centimeters. So I told you to know that one. All right, so now we want to do some basic, maybe 1 conversion factor at a time, maybe 2, and practice this canceling of units using the conversion factor method and having the denominator have the unit you want to cancel. So you can pull out from your handout, if you have that, sample exercise number 7, and we'll start with this. Rattlesnake is 2.44 meters long. How long is this in centimeters? So what do I want? What is it that I want? How long is it in? I want centimeters. What am I given? 2.44 meters. So meters to centimeters is within the metric system. So that conversion is going to be treated as exact. I will not use it for conversion factors. So what will I use? There's 3. Do I know how many centimeters are in a meter? I like keeping the exponents positive, so there's 100 centimeters in 1 meter, right? I like that better than saying 1 centimeter is 10 to the negative 2 meters. I like it better. Now, if you want, instead of writing 100, you could say 10 squared. You can do that. Okay. But basically, when I do this, I see that the meters cancel. And I'm multiplying this by 100. I can just move that over. And I get that for my answer. Now, some of you are saying this is really easy. I don't need to do this. I can do it in my head. That's awesome. However, in my classes, you have to show your work. And I want you to practice with the easy ones, because then you can do the mental math to make sure you're doing it right, because you can do it in your head. So when we get to ones maybe you're not as comfortable with, you can then, know the conversion factor method. So here, the average human brain weighs 340 grams. What is this in kilograms? So I'm starting with grams. I want to go to kilograms. So for that metric conversion, so I don't use that for sig figs, I know there's 1,000 grams in a kilogram, right? Because kilogram is bigger, right? Remember 10 to the 3. All right. So what do I have to do? I'm basically dividing it by 1,000. Again, moving the decimal over 3 times. So I get 0.34. Why only 34? Why is there no 0? This is a trailing 0. There's no decimal, so we don't count it. So there's only 2 sig figs in this measurement. So we have 2 sig figs for our final answer. C, how many minutes are in 1.6 days? Okay, so now we're going from days. We can't go straight to minutes, right? So what could we do? Maybe one day is 24 hours. We can do that. And 1 hour is 60 minutes. Okay, so this isn't 1 conversion factor, it's 2, but it's okay, because we're going to start with the given 1.6 days, and we want minutes. So how do we do that? We can go from days using this conversion to hours, and from hours we can use this conversion and go to minutes. So I know I kind of did this real quick because I'm sloppy. I want you to be able to see it, but basically you're going, all right, 1.6 days is what I start with. I need to cancel out days, so that has to go on the bottom. So 1 day is 24 hours. I know this, right? And what I do is I see days cancel, I'm left with hours, but I need to go to minutes, okay? So to cancel out hours, put it on the bottom. 1 hour, 60 minutes. that cancels. I do the multiplication. I get 2,300. Why? 2 sig figs, because there's 2 sig figs in the problem. Okay. And the unit is minutes, because that's what didn't cancel out, and that's what's left over. So I have the correct number, right? And how did I get times 10 to the 3? Because I could have left it at this. I could have just left it as this. But why is it 10 to the 3? 1, 2, 3. This number is bigger than 1, so the exponent is positive. Again, all that stuff from the first lecture, it comes back here. Now with D, inches to miles, another 2 conversion factors. They're provided. So I'm starting with miles. I want to get to inches. 2.7 miles, 1 mile, it's 5,280 feet. That was given to you. You should know that. That's our system, but it's given. The miles cancel. Then I need to go, I don't want to stop at feet. I want to go to inches. So 1 foot, because I need to cancel out this unit, is 12 inches. That cancels, and I'm left with inches. Why is it 2 sig figs? Because there's 2 sig figs here. This is English to English system, English to English, so we treat it as exact. So we use the numerical value in the problem, 2.7. If you're ever lost, just use the numbers in the problem to determine sig figs. That's the easiest way. I know sometimes it's not that, but 99% of the time. So here we're still within our system, pound to ounces, tons to pounds. So here I have an object. It weighs 1.88 times 10 to the 3 ounces. How many tons does it weigh? So I start with ounces, and they tell me there's 16 ounces in a pound. So I want to put ounces on the bottom to cancel it. 16 per pound, that cancels. Then I can go from pounds to where I want to go, tons. So pounds go on the bottom so that it cancels here. In this conversion factor, I'm canceling out pounds, and I'm left with tons. Okay. And again, how are you going to multiply? You're going to multiply 1.88 times 10 to the 3. Remember to use that EE button, second function EE, right? So you would go 1.88 second function EE or EXP3, right? Basically times 1 times 1. And then when you hit divide, what I recommend is do the parentheses, 16 times 2,000, and you get this number. Now we only want 3 sig figs. So if I line 3 sig figs, these are leading zeros. They don't count. I go 1, 2, 3. So I'm stopping at the 7. This 5 means I'm going to round up. So it's 0.0588 tons. And I got 3 sig figs, the correct numerical answer in the unit. If you need to pause it, you can pause it, rewatch it, ask me questions, but that's pretty much it. Go to the last one. Now, the reason why you see this little squiggly, like not quite an equal, that almost looks like a congruent sign, but it's not. That's because this is going from the metric system to the English system. So although we don't use the 1, we would use this measurement here as sig figs, and this is 3 sig figs. But you see here, there's also 3 sig figs. So, if this wasn't provided for you, I would just use that. So you're going to have 3 sig figs for your final answer. So how many gallons of water is in 0.465 liters? So what am I going to start with? I'm given 4.65 liters, and I want to go to gallons. I know from liters, I can go to quarts, because that is right there. And I can go from quarts to gallons. How come? 4 quarts equals 1 gallon. Oh, I didn't finish this problem. I'm sorry, because it says how many gallons. So Really, what I should do is I have 4.65 liters. If I want to cancel out liter, I need to go to quarts. So 1.06 quarts in 1 liter. So that cancels out there. And then there's 4 quarts to 1 gallon. So basically, you're going to take that number divided by 4. Let me go ahead and do that, give you the right answer. I apologize. And I want 3 sig figs, and I get 1.23 gallons. So that would be my final answer. So that's kind of using conversion factor dimensional analysis when there's like 1 or 2 conversion factors. Another time where we tend to use 1 or 2 conversion factors are with percents. So a percent is basically part over whole times 100, but what we can do is we can use it as a conversion factor. So if I say this food is 15% by mass fat, what does that mean? There's 15 grams of fat per 100 grams of food. And again, I can flip that. If I'm not using the unit of grams, let's say the metric system, to weigh the food, let's say I'm using something else, like milligrams, I can still use the ratio. 15% is 15 still over 100. It doesn't matter the unit. So I can change it to milligrams as long as I keep it consistent. I can even do it for pounds if I want. Okay. So whenever I deal with percents, I should think of them as part over whole in a ratio. So 15% is just 15 over 100, right? Just like 25%, if you wanted to make it a ratio, is 25 over 100. So the human body is composed of 65% oxygen. How many kilograms of oxygen are in 86 kilograms, right, of a man? The 65% basically means 65, right, oxygen per 100 of body. Now the unit, how many kilograms of oxygen in 86 kilograms of man? Okay, so I'm starting with 86 kilograms of man. So in 100 kilograms, there's 65 kilograms of O2. And for sig figs, this is actually 3 sig figs, so I should have written 65.0, but that's okay. My final answer only has 2 sig figs because the 86 and this only has 2 sig figs. So that works out. Here's another one. A typical intravenous saline solution contains 0.90 sodium chloride, so 0.9% sodium chloride. If the total bag contains 1 kilogram, how many grams of sodium chloride does it contain? So this is giving me what? It's a little confusing here because I see 2 numbers, so students get confused. The key is this is a percent. So what does that mean? It means it's a ratio. There's 0.9 of something of sodium chloride per 100 intravenous solution. So I'll just put solution. That's why I got the picture of the IV bag. Okay. If the total bag contains, so what am I given? I'm given 1 kilogram of solution. And I want grams of sodium chloride. Okay. So how am I going to do that? From kilograms of solution, I can go to kilograms of sodium chloride. How come? There's 0.9 kilograms of sodium chloride per 100 kilograms of solution. And then from kilograms, I can go to grams because of the metric system. In 1 kilogram, there's 1,000 grams. Yeah. Here's another way. What I did is I converted the 1 kilogram first to grams, 1,000, right? So 1 kilogram is 1,000 grams of solution. And then once I had it in grams, I used the same ratio and just said 100 grams of solution gives me 0.9 grams of sodium chloride. And I want 2 sig figs because the percent has 2 sig figs, is the leading zero. So I get 9.0 grams of sodium chloride. So you can do it that way because kilograms of solution cancel. I have grams of solution, that cancels. Or what I said earlier, where you would go 1 kilogram of solution, right? There's 100 kilograms of solution per 0.9 kilograms of sodium chloride. And then in 1 kilogram of sodium chloride, there's 1,000 grams of sodium chloride. You get the same number. Why? Because you're going to take 0.9 times 1,000 like we did here, and then 100 times 1 in the denominator. So you get the same numbers. I'm just making sure I cancel the units correctly. And I do, and there's more than one way to do it. So here's kind of a bigger challenge, right? Right. So here's kind of a big challenge. Perform the following conversions. A dental amalgam used in fillings for teeth contains 44% mercury. How many milligrams? So it's probably by mass. So it's 44% mercury by mass to 100 of the amalgam, right? How many milligrams? So what do I want? I want milligrams of mercury. Milligrams of mercury are in 75 ounces. Oh, okay. Of amalgam, right? So I have ounces. What am I going to do? I got to go from ounces right here. I can go from ounces to pounds. And then from pounds, I can go to grams. And now this is going to be grams of amalgam, right? Then I can go to milligrams of amalgam, right? Because there's 1,000 milligrams in 1 gram of amalgam. And then I can go from milligrams of amalgam to milligrams of mercury using the 44%. Now, I could have done the 44% earlier. It really doesn't matter. In this example, I just chose that. So the answer is that. Let me write it out for you. 75 ounces of amalgam. There's 16 ounces per 1 pound of amalgam. Where did I get that? Right there. Ounces cancel. I'm left with pounds. I don't want pounds. I need to get to the metric system, right? I'm still in the English system. How do I get to the metric system? Right here. I'm using this English conversion of mass to get to grams, which is a metric conversion. So I need to get rid of pounds. So I put that on the bottom. 1 pound is roughly 454 grams. And this is still of the amalgam. Right? Because the amalgam, it's a mixture, it's an alloy. 44% of it's mercury, and the rest might be silver or some other type of metal, right? So 44% out of the entire 100 is the mercury. And then I want to go from grams to milligrams. So they're in 1 gram of the amalgam. There's 1,000 milligrams of amalgam. Earlier, the pounds had cancel, now the grams cancel, but I still have the amalgam. I haven't converted to mercury. That's where the percent comes in. So in 100 milligrams of amalgam, right, there's what? 44 milligrams of mercury. And that should give me this answer. Okay. That's a lot of mercury. An amalgam's not going to weigh 75 ounces. That's pretty heavy. If 16 ounces is a pound, you're not going to get pounds of a filling in your tooth. So I should have checked the numbers a little bit better, but you get the idea here. Okay. So in this particular conversion factor, we had to use 4, and sometimes the problems do require more than 1 or 2 or even 3. So I like to give you examples of, multiple examples. So I talked about percents, but there's also, we've heard parts per million and parts per billion. So parts per million is ppm, right? So, maximum amount of mercury in tuna, since we talked about mercury, from the Environmental Protection Agency, that's what EPA stands for, is 0.5 parts per million. So that means there's 0.5, I put lead here, it should have been mercury, my bad. 0.5 grams of mercury per million grams of tuna. So that's why it's 10 to the 6. So for parts per billion, right? So there's contaminant levels in water. So antimony, elemental symbol SB, okay? So the most we want is 6 parts per billion. So that means 6 grams of antimony, elemental symbol SB, per billion grams of water, okay? So we could do those conversion factors, the same as we did, so if I wanted to use the example, if it said 6%, it would be 6 grams per 100 grams. If it was 6 ppm, parts per million, it'd be 6 grams per 10 to the 6. If it's 6 ppb, now we're doing 6 grams per 10 to the 9. So instead of doing 10 to the 2nd grams or 10 to the 6 grams for parts per million, now we're doing 10 to the 9 because it's parts per billion. I know this is a lot. If you want, you can definitely pause it, stop it, watch it at a different time. I'm going to just push through, and I'm going to cover the topics of density because it'll help me with my last few types of calculations in a sample set of 9. So density, right? Does something sink or float in water? Well, that is determined based on whether or not it has a smaller or greater density of water. You may have used, as a kid, a density gradient where you use different liquids and layer them upon each other. That's also dependent on polarity, but for the most part, the most dense would be on the bottom, the least dense would be on the top. So density typically is mass per volume. It's that ratio. So I tell students, think of it as DMV, right? DMV, right? So mass over volume. And the units for mass is grams, and the units for volume is milliliters, okay? Typically, when we're talking about solids and liquids. Now, solids and liquids are referred to as condensed phases because their volumes are fixed, because the particles are close to each other. Gases, you're going to see densities more along the line of grams per liter. Why? They are not condensed. The particles are far apart from each other, so you need a much larger volume, like liters instead of milliliters, to get any type of mass. The other thing you might notice is I've used interchangeably centimeter cubed, okay? Why is that? Well, for volume, there's a direct measurement, like I could take this cube and measure the length, the width, and the height, right? And if I look at it, there's each cube in here is 1 centimeter. So the length here is 1 centimeter. The length here is the length is 1 centimeter, the width is 1 centimeter, and the height is 1 centimeter. So if I plugged it in, 1 centimeter by 1 centimeter by 1 centimeter would give me a volume of 1 centimeter cubed. And if I was to pour water into that, that would give me 1 milliliter. So 1 milliliter is 1 centimeter cubed, right? And you may have heard this if you watch TV shows or you work in a hospital. If you look at anytime there's any type of injection or some type of oral consumption, cc, cubic centimeter, centimeter cubed, cubic centimeter, 10 cc's means 10 milliliters, okay? So another thing is, if I look in this example, I have 10 of these cubes and I have 10 centimeter. The width is 10 centimeter. The height is 10 centimeter. If I did that, 10 centimeter by 10 centimeter by 10 centimeter would equal 1,000, because 10 times 10 times centimeters cubed, and that's equal to 1 liter, because remember, a centimeter cubed is the same as a milliliter. There's 1,000 milliliters in 1 liter. So if you have a perfect cube, you can take a ruler, measure it out, and do the volume using length times width times height. And you can use what's called the direct measurement. But what if it's not a perfect cube, or it has an irregular shape? What do I do then if I can't use a direct measurement? Well, we can do volume by displacement. So what do I mean? So like this cylinder is bent, it's chipped, right? If I had a perfect cylinder, I could still, if I had a perfect cylinder, I could use direct measurement, because the volume of a perfect cylinder, I would take the area of the base, the area of the space, it's a circle, is pi r squared. R stands for radius, that's why I drew the radius, squared times pi. And then I can measure the height, and I can multiply it by the height. And the radius squared could be like centimeter squared, which is area, because I'm taking the area of the base, and I'm timesing it, because area is length times width, you can think of. And I'm timesing it by centimeters height, I would get centimeter cubed. But if it's all bent, that doesn't help me. So what can I do? Well, I can take an initial volumetric measurement of, let's say, water. And I can drop the irregular shaped object in the water, and it's going to displace it. It's going to shift it up because it takes up space, and that space is going to be measurable, because then I can take a final volume. So I can take an initial volumetric measurement and a final. And that displacement, that difference right here, I can subtract, and that'll give me the volume of the irregular object. So this is volume by displacement. You have to make sure that once you drop the object, it's completely submerged. You know what I mean? So you have to make sure of that. You also have to do your volumetric measurements. You have to record them at eye level, and you have to read, there's a curvature here. It's called the meniscus. I'll spell that for you. And you have to read the bottom of the meniscus, the curvature. You have to read the bottom of it. And you have to read it at eye level and have it on a flat surface for it to be accurate. But that's what you do, right? You take an initial volumetric measurement on a flat surface, drop down to eye level, you read the bottom of the curvature, then you take the object, you carefully place it so it doesn't splash everywhere. Typically, you take it at a 45-degree angle and slide it down also so it doesn't break the glass. And then you do your final volumetric measurement. So the difference, and now we're using rules of sig figs, we get, 9.5 mils. Now, some people might go, hey, that's only 2 sig figs. This has 3, this has 3, it should have 3. Nope. Remember, with addition and subtraction, we go to the least precise or I said the placement value. Both of these end in the tenths. So my final answer has to be the tenths. So you can actually have less sig figs when you do addition and subtraction because we're using precision of the instrument, okay? So I only have 2 because I can only go to the tenths with, confidence. And then here they use it interchangeably with centimeter cubed. So how do I get the density by this displacement? Well, remember, density is dmv. I have the volume, now I need what? To mass the cylinder, right? You got to make sure it's dry. I would mass it first and then insert it in the water. If you did it the other way, you got to make sure this is dry. If you put it on a weigh boat, these are called weigh boat or weighing trays, make sure you tari it, zero it out when you put the tray on, and then take the measurement. But then you can get your mass, 68.60 grams. This has 4 sig figs. Why 4? That's a trailing 0 with the decimal, it counts. This has 2, but now I'm doing multiplication and division. So I picked the fewest sig figs. 2 is less than 4, so it's 7.2 grams per centimeter cubed would be the density of this object here. And you actually do this in lab. Typically, this is your first lab in a high school lab or introductory chem lab or a preparatory chem lab at any college. It's even for the general chem science majors, you typically have a density lab right off the bat. Now, again, I want to go back to densities because what we notice is, your solids, grams per mil, your liquids, grams per mil, but your gases, the unit, grams per liter. You need a lot more, a much larger volume to get any type of mass because the majority of space is empty. The other thing I want you to notice is water. Water's got an excellent density. It's 1. It's probably the one you want to know because, you compare everything to water. Will it float? Will it sink? Well, if you know that the density of water is 1, that's easy. Like olive oil, it's less than 1, so it's going to float, right? If I took a silver coin, it's got a density of 10.5 grams per mil. That's much greater than 1. It'll drop down, right? So I could use that as a reference point. So why am I doing that? Well, the last problem solving that we're going to do is sample exercises 9. We're going to continue our conversion factor method, but now we're going to use density because remember, density is a conversion factor. It allows me to convert mass to volume or volume to mass if I need to by simply flipping the density ratio to cancel out the units. So ethylene glycol is used as antifreeze in cars and has a density of 1.11 grams per mil. What is the mass in decigrams? So I want decigrams if I have 75 mils of ethylene glycol. By the way, ethylene glycol and antifreeze, it has 2 carbons, and then it has 2 alcohol groups, and then the rest are hydrogens. Now, you don't need to know that, but it is a main component in antifreeze. Okay, so what that does is it raises the boiling point so it doesn't boil as fast in your radiator and keeps it liquid to keep the engine cool. And so it raises the boiling point, makes it higher than 100 degrees Celsius, and it lowers the freezing point. So that's why we use it. But going back to this, a lot of people would say, all right, if I want decigrams, what do I start with? I have 2 numbers. I have 75 mils and I have the 1.11 grams per mil. Well, this is not a ratio. If I don't end with the ratio, I shouldn't start with the ratio. This is actually a ratio. Density is a ratio, converts mass to volume. So if I don't end with a ratio, like let's say I had miles per hour, that's a ratio. I can start with the ratio like meters per second, because meters per second is a unit of distance over time. Miles per hour is distance over time. But that's not what I have. I just have decigrams. So if I don't end with the ratio, I don't want to start with the ratio. That makes it a lot easier. I'm going to start with 75 mils. So if I start with 75 mils of ethylene glycol, what can I do? I can go from the mils of the ethylene glycol to the grams. And then from the grams, I can use the metric system because I know there's 10 decigrams in a gram, 10 years in a decade, and I can go to grams. Oh, sorry about that. So we see it right here. I start with 75 mils. In 1 mil from the density, there's 1.11 grams. There should be a 1 there. And then in 1 gram, there's 10 decigrams of the ethylene glycol, and I get 825 decigrams. So how many sig figs for my final answer? This is a measurement, so I use 3 sig figs. This is a measurement, that's a trailing 0 after a decimal, so it counts, so that has 3 sig figs. So my final answer has 3 sig figs. So I actually use the density as a ratio to cancel out the volumetric unit of milliliters to get me to a mass measurement of grams, which I can then convert grams using the metric system to decigrams. What about this one? The density of blood plasma is 1.03 grams per mil. What is the mass in kilograms in a gallon of blood? Okay, so what do I want? Mass in kilograms. I don't end with the ratio, so I shouldn't start with 1. So what am I given? I know I'm given gallons per 3.785 liters. I'm given 1.03 grams per mil, but those are ratios. So what am I going to start with? I'll start with a gallon of blood. Ooh, I said that like a vampire. Blood. So that's the final answer. Let's work it out. I have 1.0 gallons of blood. In 1 gallon of blood, I put this on the bottom, there's 3.785 liters. This is 4 sig figs. I don't count the 1. Why am I using this for sig figs? Because I'm going from English system to the metric, okay? We'll see, we won't need it because there's only 2 in this number, but I'm just reviewing. Gallons cancel. Then I need to get to milliliter. Why do I need to get to milliliter? Because that's when my density is in, and the density will give me grams. So in 1 liter, there's 1,000 milliliters. So what I'm doing, I'm converting the volume of gallons of blood to milliliters of blood. How? Gallons to liters, liters to milliliters using what? The metric system. Now that I have milliliters, this is why they give me density, because density is grams per mil. It allows me to convert the volume to the mass. How? In 1 milliliter of blood, there's 1.03 grams of blood. That allows me to cancel out the milliliters. Now I have mass. That's what density does, volume to mass. This is 3 sig figs. And then last but not least, there's 1,000 grams in 1 kilogram of blood. So grams cancel. I'm left with the units of kilograms. I have 2 sig figs because I started with the smallest. And when I'm calculating this, there's 1,000 in this numerator and then this denominator, so you don't need that. You can cancel those numbers out when you're punching it in on your calculator if you want to be fast and efficient, because fluency is important, right? How quick you are. So I would take the 1, times it by the 3.785, times it by the 1.03, and that should be my answer. Which makes sense. 3.785 times a little more than 1 gives me 3.9. Okay. So another type of calculation would be, all right, in ultrasound, sound waves travel through liver tissue at a rate of 1,540 meters per second. There's 3 sig figs. This right here is a trailing zero, it doesn't count. Meters per second is a velocity. Why? Distance over time, speed. How many centimeters? So what do I want? I want centimeters. Okay. Will the wave travel if I start with 23 microseconds? So I have 23 microseconds. So I need to go from time to distance. That's why I need a velocity or speed, because it's distance over time. I have microseconds. I can convert that to seconds. How? There's 1,000,000 microseconds, or 10 to the 6 microseconds in 1 second. That's one of the metric prefixes we went over. Okay. In 1 second, there's 1,540 meters. In 1 meter, there's 100 centimeters. So this is showing you how, right? What distance through liver tissue will this wave travel in 23 microseconds, traveling at this speed, the sound wave, right? So we see that microseconds cancel, seconds cancel, meters, I'm left with centimeters, 3.5 centimeters. So that is the end of the chapter 2, which is basically your chemistry, math concepts, where we use our conversion factors, our different units of measurements, and our sig fig rules to solve problem solving. Typically, this takes a while. That's why I give students more than a week in this class to go over it. But if you keep doing it, following this method, you should be successful. So again, this lecture covered the different types of measurements, the metric system, our system, and converting between the English system and the metric system to perform dimensional analysis, which is word problems, using the conversion factor method. I hope it was helpful, and thanks for watching. Let me know if you have any questions.